Welcome to Wildcat Science with Mrs. Haugo. This is Chemistry, Chapter 10, Section 4, Part 5. And today, like I said, we're going to be going on Section 4, which is Chemical Reactions and Energy. So every chemical reaction involves the breaking and forming of chemical bonds. So we know that bonds store chemical potential energy. And breaking bonds, if you're going to break them, it requires energy to break that bond. And forming bonds releases energy. So the question is, which one is more? So to break a bond, it's going to take some energy. And then when you form a new bond, it's going to release energy. If it releases more energy by forming new bonds than it absorbed by breaking the original bonds, then it's an exothermic reaction. If it releases more than it absorbs, it's exothermic. If it releases less energy than it absorbed, then it's an endothermic reaction. So the overall, it is either releases more overall or absorbs more overall. Exothermic and endothermic. Okay, for example, a hot pack uses chemical reactions to release heat. So that would be an exothermic reaction. A cold pack uses chemical reactions to absorb heat. And that is also a chemical reaction. That one's an endothermic reaction. We're going to talk about a new term here, enthalpy. Enthalpy is the energy potential of a chemical reaction. Like how much energy does it give off or does it take in? The enthalpy. And since enthalpy is talking about energy, it's measured in joules. And we're always talking about not the absolute amount of enthalpy, but the change in enthalpy. And it is delta H. I don't know why. E was already taken for energy. So the change in enthalpy, or delta H, measures the amount of energy absorbed or the amount of energy released during a chemical reaction. So if delta H, the change in enthalpy, is negative, it's an exothermic reaction. And this makes sense because if it's exothermic, it released more energy, so the products have less energy. So if you're minusing, let's see if I can get my hands in there. If you're minusing a smaller number minus a bigger number, you're going to get a negative number. But what happens if the delta H is positive? Well, then it is endothermic. So it has absorbed more energy and the products are at a higher state than where you started. So a bigger number minus a smaller number is going to be a positive number, endothermic. So a thermochemical equation is a chemical equation that includes information about the energy released or absorbed by the reaction. So it's a balanced chemical equation, plus it tells us, often tells us the change in enthalpy. And the energy absorbed or released depends on the moles of the reactants. So if I have twice as many chemicals, I'm going to release twice as much energy. So that makes sense. So please write down this example. Solid carbon reacts with oxygen gas to form carbon dioxide gas, and there's a change in enthalpy of negative 393.5 kilojoules. So is this reaction endothermic or exothermic? It is exothermic. It has a negative change in enthalpy. It gave off energy. Whereas if we have twice as much carbon, twice as much oxygen and twice as much carbon dioxide, we're going to have twice as much energy released. So maybe a little fire versus a big fire. Delta H equals negative 787 kilojoules. All right, so please write those down. And we know that energy cannot be created or destroyed. Energy is always conserved in chemical reactions. So, given that, what's the change in enthalpy, the delta H, of this chemical reaction? Carbon dioxide gas decomposes into solid carbon and oxygen gas. What would be its change in enthalpy? So you have to use the equations above to be able to answer that question, and we'll discuss the answer in class. All right, so let's talk about, it's related to enthalpy and change in enthalpy, but it's the enthalpy of formation. And the way we write it is delta H with a little subscript F. That is the change in energy when 1 mole of a compound is assembled from its pure elements. So the change in enthalpy when you form something. So this is used in calculating the change in enthalpy of any reaction. The values were found experimentally, and we find them in tables, like in your book on page 312. When we are finding the change in enthalpy of a reaction, we're going to be using Hess's law. So please write this down. So the change in enthalpy, delta H, is equal to the sum. So this is a capital Greek letter sigma, and that stands for sum. So the sum of the change of enthalpies of the products, notice products are first, minus the sum of the, I misspoke here, the enthalpies of formation. So the enthalpies of formation of the products, and then the enthalpies of formation of the reactants. So the change in enthalpy is equal to the sum of the enthalpies of formation of the products minus the sum of the enthalpies of formation of the reactants. All right, please write that down. Let's talk about what that means. So when we're calculating using Hess's law, the change in enthalpy, we're going to make sure to multiply these enthalpies of formation by the coefficients found in the chemical reaction, because it matters if in a reaction there are 6 moles or just 1 mole. So for each enthalpy of formation for each product, we're going to take the coefficient in moles times the enthalpy of formation. So I think it'll make a little more sense once we kind of go through an example together. A couple more things about it before we do that example. Enthalpy is conserved in a chemical reaction. So no enthalpy will be created, no enthalpy will be destroyed. Whatever is lost somewhere has to be gained somewhere else. And enthalpy is a state function. What does that mean? That means the change only depends on the initial and the final. It doesn't matter how you get there, just where you started and where you ended. That's the only thing that matters. So a state function only matters if where you start and where you end. It doesn't matter the path that you take. So please make this drawing in your notes. We have enthalpy, and there are 2 ways to get there. One way, we go straight from the reactants to the products, and the enthalpy is this change right here between the reactants and the products, the difference between the products and the reactants. And then in another way, we go down here to one compound, and we come up here to this other compound, and then we finally get to the products. So this pathway is different than this pathway, but they have the same change in enthalpy. So only the beginning and the end matter. Okay, so let's move towards that example I promised you. How to solve an enthalpy problem. So please write these down. First thing you need is a balanced chemical equation. It needs to be balanced, otherwise everything else, you'll get the wrong answer if you don't start with a balanced chemical equation. Then you need to look up all of the enthalpies of formation. Sometimes you'll see them referred to as heats of formation of all of the compounds and elements in the equation. A pure element, its enthalpy of formation is going to be 0, so it may not be listed, but it's 0. Then you're going to multiply the enthalpy of formation by any coefficients in the balanced chemical equation. Okay, then we're going to write down the equation and sub in our numbers and get an answer. So delta H is equal to sigma, the moles or the coefficients of each compound, times the change in enthalpy, and we do all of the products first, minus the sum of all of the coefficients times the enthalpies of formation of all the reactants. Whew. All right, so please write this down. Now let's look at our example. If the standard enthalpy of formation of solid glucose is 1,266 kilojoules per mole, what is the change in enthalpy when 1 mole of glucose is consumed during cellular respiration in your body? So please write down the question. Okay, I'd like you to take a moment and think about what are the products and the reactants of this process, the chemical reaction of cellular respiration. Well, we know that there is glucose. Our body consumes glucose. This happens in the mitochondria. And we know we need oxygen. So those are reactants. And what do we give off? Carbon dioxide and water. So if you wrote down glucose and oxygen in your reactants and carbon dioxide and water in your products, good job. So let's think of states of matter. Glucose could be solid or aqueous, and we know things in our body, reactants in our body happen in aqueous conditions. So let's say it's aqueous, and we know oxygen is a gas, we know carbon dioxide is a gas, and we know water is liquid. Our next step is to balance it. So please take a moment and balance your chemical equation. So hopefully you've already tried that. If not, pause the video and we'll double check it. So we're going to start with carbon because the other options are hydrogen and oxygen, and we know we don't start with those. So carbon, there's 6 here. So I'm going to put a coefficient of 6 in front of the carbon dioxide. So now I have 6 carbon dioxides, and then oxygen is in 2 places here, so that's not so good. So we're going to do hydrogen next. There are 12, so I come over here, and they come in pairs of 2. So then we're going to have 6 pairs of 2 to equal 12. And then I go to oxygen. So this one is alone, so I'm going to do that side last. So 6 times 2 is 12, plus another 6 is 18. So I come over here, I need 18 on this side, I have 6, so 18 minus 6 is 12, and so then I need 12 here, and they come in pairs, so I need a coefficient of 6. So if you got that right, good job, and if not, you want to change it. And also mine is being a little bit ornery. So let's get that 6 in there. Okay, so your next step is to look up all the enthalpies of formation for your different compounds. They tell us glucose right here is 1,266 kilojoules per mole. So please take a moment and look up all your enthalpies of formation for your different compounds. Okay, well, hopefully you've taken a minute and written down all of your enthalpies of formation. As we talked about, glucose is negative 1,266 kilojoules per mole. And we know oxygen is a pure element, so it's going to be 0. Carbon dioxide, negative 393.5 kilojoules per mole. And water, liquid water, is negative 285.5 kilojoules per mole. In our next video, we're going to set up the problem using Hess's law, using that equation, and solve it. I will see you then. Bye.